Hello everyone, I'm Yunfei, and today I'm here to present to you our new project, RFind, to mine the billions of deployed RFIDs. And this is a joint work with my colleagues, Nick and Fado from MIT Media Lab. So this talk is about localization. At this point in time, in the audience who has not heard about localization? Okay, good. Fado, do you know about localization? You do. Awesome. So the goal of this talk is to achieve the most powerful form of localization on the simplest possible device. And now you may be wondering, what is the most powerful form of localization? It's a localization that can get you extreme accuracy and also make no restrictive assumptions. For example, the most expensive radar, which is used by military, can achieve millimeter accuracy level without even knowing where the target is. Now, what is the simplest possible device? It's a battery-free RFID sticker like the one shown in my hand. And today, this sticker can operate without the use of a battery, and they cost only from 5 to 10 cents each. And the way they work is, you have a wireless device called a reader, and the reader will shine a wireless signal to power up the RFID, and it will respond with its unique identifier. So how can we bring radar capabilities into this battery-free RFIDs? To answer this question, let's first take a look at how radar systems work. A radar will transmit a very short pulse, and it will measure the time it takes for the pulse to get reflect and come back. And we call this round-trip time the time of flight. If I know the time of flight, I can easily compute the distance because I know that the distance is equal to the time of flight times the speed of light. So in order for me to bring radar capabilities into battery-free RFID, it looks very simple, right? So why not just have a reader and transmit a very short pulse and to measure its reflection from the RFID? Unfortunately, however, this would not work. Because if you want to do that, you cannot power up the RFID, and you cannot get a response. The reason is that today's RFID cannot be powered from a very short pulse. And because of this problem, pulse RFID localization always assume various restrictive assumptions in order for them to localize. But in this talk, what I want to do is I want to address this challenge directly. So in this talk, I will present a system called RFind. RFind brings radar capabilities to billions of deployed RFIDs. And RFind allows us to accurately measure the time of flight in indoor environment, even with dense multipasses. And finally, we implement and evaluate a prototype of RFind in real environment. And now, in order for me to do this, we must first understand where does radar's resolution comes from. The very high resolution of radar comes from its ability to use a very narrow pulse and to measure the time at a very fine granularity. If I can measure the time of flight at a very fine granularity, I can know the distance very accurately. Alternatively, I can do this in frequency domain. So instead of transmitting a very short pulse, I can transmit and measure the signal at a broadband signal. And by using that, I will be able to estimate the time of flight accurately. And this is because that the signal in time domain is inversely related to the signal in frequency domain. So now, maybe I can ask my question in a different way. Can we achieve wide bandwidth on battery-free off-the-shelf RFIDs? But the problem is, it's not that simple. So the problem is, today's battery-free RFIDs are designed to only respond to a single tone within a very specific narrowband frequency. So for example, if I have an RFID tag, if I transmit a frequency inside the ISM band, I can power up the RFID, and I can get the response from the RFID. But instead, if I transmit the signal at another frequency, which is significantly outside the ISM band, what will happen then? I cannot power up the RFID, and I will not be able to get a response. The problem is, Battery-free RFID today are optimized to harness power from signals within the UHF ISM band, and the bandwidth is very narrow, and it becomes very difficult for me to estimate the time of flight accurately. So are we doomed? Because we can neither power up the RFID using a very short pulse, nor a wideband signal. To address this problem, we will present a system called RFind. RFind is built upon a key realization that we made about the physics of how RFID operates. So the realization is RFID modulation is frequency agnostic. And now let me explain to you what I mean by that. What I show here is a simplified schematic of an RFID circuit. It has an antenna, a power harvester, a switch controller, and an antenna impedance switch. In order for an RFID to reflect signal, it biases its antenna switch into two states, on and off, to reflect bits zeros and ones. So when the antenna switch is turned off, it is as if there is an open circuit between the antenna and the ground. So when the signal comes in, it can flow into the power harvester to power up the RFID. On the other hand, when the switch is on, it is as if there is a short circuit between the antenna and the ground. So when the signal comes in, it will bounce off the ground and gets re-radiated out from the antenna. So the physics, to understand the physics, here is a very simple analogy. The way an RFID modulates the signal is like a mirror. So when the switch is off, it's like the mirror is pointed away. So it won't reflect any signal. On the other hand, when the switch is on, it's like now the mirror is facing to me, and signal will get reflected back. And now the mirror analogy is really nice, because let's say if I have another signal at a different frequency, when the switch is off, the signal will also get the signal also won't get reflected back. However, on the other hand, when the switch is on, the signal will get reflected back. And that's what I mean the RFID modulation is frequency agnostic. Of course, this is only true that if we can power up the RFID in the first place. Said differently, this can only work if I can somehow turn the mirror on and off in the first place. So to be able to sense over a wide bandwidth and power up the RFID, in this talk, I will present a new technique which is called dual frequency excitation. The dual frequency excitation is a technique that decouples power delivery from sensing in RFID localization. So remember that the problem is today's RFID are optimized to only harness power from signals within the UHF ISM band. For example, if I have a signal within the ISM band, I can get a response. But if I have a signal outside the ISM band, I cannot get a response. So here is our idea. What I want to do here is I want to transmit two frequencies simultaneously. One is inside the ISM band, and the other one is outside the ISM band. So I will use the frequency inside the ISM band to power up and communicate to the RFID. And once the RFID is powered up, I will use another frequency outside the ISM band to sense the reflection. And remember that this is because RFID modulation is frequency agnostic. However, only one frequency is not enough. In order for me to obtain a wide bandwidth, I will vary the sensing frequency over time in order for me to get a wide band. So basically, the idea is to sweep the frequency over time to emulate a very large bandwidth. And after I get a wide band, I will be able to estimate the time of flight accurately, which will finally lead to accurate RFID localization results. However, there is one more problem, which is the FCC regulation. FCC only allows us to transmit high power within the ISM band. However, outside the ISM band, the frequency emission limit has to be more than 10,000 times lower. What is really nice about dual frequency excitation is that it allows us to be FCC compliant. Because the powering up signal is within the ISM band, we no longer need a high power transmission in order for us to sense the reflection. And we can transmit the sensing frequency even below the FCC mask, in order for us to get the reflection. And over time, we will sweep the frequency in order to us to emulate a large bandwidth. So again, the idea here is we will transmit an extremely low power sensing frequency and sweep them over time in order for me to get a very large bandwidth. And now I have to explain to you how can I use dual frequency excitation in order for me to obtain a broad bandwidth operation. And the next, I want to tell you how can we move from this wide bandwidth to accurate time-of-flight estimation. So we know that with a wideband signal, we can use them to estimate the channel taps in time domain. And this is typically done using inverse Fourier transform. And the output, what I show is the output. And the output is a power as a function of channel taps in time domain. And here, I will have different multiple peaks. This is because that instead of just having the direct path, I will also have other multipath reflection. But as we know that the direct path travel the shortest distance compared to other multipasses, this allows me to filter out all the other multipasses and for me to get accurate time-of-flight estimation. However, here is one more problem, which is the exact peak location is still impacted by noise and leakage from other multipasses. In order for me to get even better localization accuracy, and in our paper, we introduced a super resolution algorithm, which basically uses the multipath suppressed phases in order for us to achieve even a much higher localization accuracy. And for the sake of time, I will not go into details, but I'm very happy to take questions afterwards. So we implement and evaluate RFind. So for the reader, it's implemented on the USRP software radio platform, and we use two USRP for TX, one to transmit high power inside the ISM band, and the other one transmit low power outside the ISM band. And in order for us to get 3D localization result, we use three USRP as a receiver. And our system is compliant to EPC Gen 2 RFID protocol and FCC regulations. And we evaluate our system on various off-the-shelf battery-free RFIDs. And we test our system in real indoor environments. And for the ground truth, we use a laser pointer to measure the ground truth. And now let me show you some of our evaluation results. So the first question is, how much bandwidth can RFind emulate? So what I show here on the y-axis is signal-to-noise ratio, and on the x-axis is the frequency. So a typical RFID communication bandwidth is about 40 kilohertz. Even if you try to hop the channel inside the ISM band, you can get at most 26 megahertz. But in RFind, we can achieve more than 300 megahertz bandwidth. So the SNR drops a little bit to the edge is because of the reader antenna. And there is some fluctuation in our measurement, which is caused by the RFID antenna mismatch. So what is really interesting here is we can achieve a very high SNR despite the fact that we transmit the sensing frequency at a low power. The reason is that in RFID, the noise flow is determined by self-leakage. So when you reduce the sensing frequency, you also reduce the noise flow in your receiver, keeping the SNR unchanged. So the take-home message here is we can achieve a high SNR over a wideband despite the ultra-low power of sensing frequency regulated by FCC. So next, I will show you our accuracy as a function of bandwidth. So what I show here on the y-axis is the arrow, on the x-axis is the bandwidth. And the purple indicates the results derived from the direct time of estimation, and the green indicates our results after super resolution. So with ISM band only, as you can see, we can only achieve a localization accuracy up to a few meters. But the localization accuracy will improve dramatically as the bandwidth increases. And in our case, in RFind, after 200 megahertz, we can achieve not only median error, but also 90th percentile error in sub-centimeter scale. And because of the broad bandwidth, we can achieve very accurate 3D localization accuracy. What I show here is the CDF as a function of absolute error for 3D localization. And as you can see, in RFind, we can achieve a median error smaller than 1 centimeter and a 90 percentile error smaller than 3 centimeters in all X, Y, Z directions. So, which means, what does this mean? This means that we can achieve sub-centimeter localization on the off-the-shelf battery-free RFIDs despite their very narrow bandwidth. And now, let me show you a video of how our system operates. And in the video, I'll put an RFID tag on a facial cleanser, and by accurately measuring the time of flight, I will be able to pinpoint the exact location. And on the upper left corner is the UI output. And our localization result will be indicated by a blue dot. As you can see, after a couple of seconds, we will be able to pinpoint the exact location of this RFID. And now I will move this bottle inside the box, which cannot be seen from a camera. As you can see, our system is able to find the accurate location of this tag. And what is really interesting is that our system is very robust. So even if a person standing in the middle, which creates a lot of multipass, our system is still able to accurately localize the position of the RFID tag, as shown here. So RFID localization has been extensively researched over the past 10 years. So past approach generally fall into two broad categories. The first category, they require you to design a specialized ultra-wideband in order for you to accurately localize the tag. However, the problem is that they cannot work on the billions of RFID tags that has been already deployed. The second approach can work on off-the-shelf RFID tags, but they assumes various restrictive assumptions. For example, they either require you to furnish the entire environment with many reference tags, or they require tag or reader motion in order for them to mitigate the multipass. And in contrast to all-pass work, RFind can achieve the best of both worlds. It enables us to achieve time-of-flight-based accurate estimation on off-the-shelf RFIDs. And also, RFind can operate without any restrictive assumptions. So you may notice that in the previous video, it still takes a couple of seconds for us to compute the exact location. And here I will show you another video about how we can achieve real-time time-of-flight positioning. This is an unpublished work. So as you can see, what I show here, so here is the antenna, and here is the output screen. And one of my colleagues is now trying to use RFID to draw in the air. So our system, and as you can see, our system is able to accurately compute the time-of-flight-based localization in real time. And what he's trying to draw is the letter ML, which stands for Media Lab. So to conclude, in this talk, I present RFind, which brings reader capabilities to off-the-shelf battery-free RFIDs. RFind can achieve very high accurate time-of-flight estimation despite the narrow communication bandwidth on off-the-shelf RFIDs. And with this capability, RFind can enable many applications, for example, quality control, virtual reality, and robotic manipulation. And with this, I will wrap up my talk, and now I'm very happy to take questions. Thank you so much.